Let me see how far up I can go. This can go not too far. Okay, so let's start. We're going to continue our lecture on training models. Why is my how did this change to happen? How did that happen? The slides are not showing on Zoom? Folks on Zoom, can you see the slides? No? So, okay. Can you see the slides now? They still can't. Okay, now they can. Now they can. All right. Oh, I see. Okay, they're unable to see the slides on Zoom. The slide is not shared. Any change? So the slide is still not being shared. Please bear with us, folks. Technical issues.
Going crazy. Can't show the slides.
Yeah. Well, something happened to my computer. It was displaying right now. What happened? Oh, jeez. So does somebody have a different laptop? Okay. My laptop has gone bad now. Does it have an HDMI? Unfortunately, I don't have the PowerPoint, so let me see if I can reboot this guy and drop the PowerPoint in Discord. That's what I need. So folks, please bear with us a minute. We're having a combination of Zoom and laptop issues. Connect this in here. Some question coming up. Come on. I didn't put the PPT, I just had the. Yeah, but the PDF has got a lot of unnecessary stuff. I'll just drop the slides on Discord. Why is this not coming up? Okay. Get the slides? Yeah. I just drop it there. Yeah. Or I just connect yours. Sorry about this, folks. We have this happen once a semester at least. Okay. Yeah. And can we see this on? Oh, fantastic. The clicker is bad. Okay, switch it.
Keeps forwarding.
All right, I switch it off. So get rid of the clicker. This is not the clicker. Okay. No, I'll take care of it. This thing has to be changed. All right. 10 minutes late, but still. Is it visible on Zoom? Yes. Yeah. The slides have wait. The slides have an issue. The Dropbox hasn't synced. The version of the slides that you're going to see on the screen is different from the version of the slides on the course page, and yeah, we have some issues. But attendance poll is 728. Poll 1 is 723. 23, 2 is 724 and 725. 3 is 726 and 4 is 727. Please do not answer everything in a hurry and just, and assuming that you're then done with the class. There's no point to it. Okay. All right. So since we are 10 minutes behind, I'm going to try to see this actually. Here's what was planned for the class. We were going to actually go through backpropagation for deep neural networks. Initially, I was actually going to be going through a little recap. So here's what we saw. Pattern classification tasks that require position invariant detection are best done with scanning. And best done by scanning the input for the pattern using an MLP. But scanning with an MLP is the same as scanning sequentially with the individual layers in the MLP, and that actually gave us a convolutional neural network. So Nestor, I just wrote some poll numbers. I'll call these out again, right? The slides have not been updated for some reason, although we posted the correct slides yesterday on the course page. So here's what a CNN looked like. We had a sequence of convolution and pooling layers. And in a convolution layer, there were two stages. First, we scanned all of the maps of the previous layer and computed an affine map where the affine map shown here as represented here as the value z consisted of terms that were affine functions of regions of the input from the output of the previous layer. And then an activation map which actually applied activations to the individual terms in the affine layer. And so when you computed an affine map, here's what we had. We had, so you would have some collection of input maps over here. So those represent these guys, the outputs, which is the output of the previous layer. When I speak of maps, the other term that we often use is channel. Then corresponding to each output channel, these terms here, there would be a filter. And so the way you computed any particular channel was by applying the corresponding filter to the entire collection of input channels. So the filter itself had as many channels as the number of input channels. Within each channel, there was a rectangular pattern of weights. And no two weights need to be the same. All of these weights are different. And the way we computed it was to place the filter on the channels from the previous layer and compute an affine term, which is basically the component-wise inner product or component-wise product of the filter term and the underlying channel term, and then summing the whole lot up. And so that gave you, and we would do this, we would scan the channels of the previous layer in this manner to actually obtain the affine map. And then once we obtained the affine map, we would apply point-wise activations to compute the next activation map. Now, the way we found this is that the input maps, the input channels, are convolved with several filters to compute the corresponding output channels. So you're going to have one filter per output channel. And then subsequently from each output channel, we're actually going to get the corresponding output activation map. So this is our first poll. The poll number is not 632. It is 723. Let me correct this online. I'm scared to do anything here because things kind of tend to break. So I don't know if you can see the board. It is 723. Again, I apologize for rushing through the lecture today because we just lost 10 minutes to a bad laptop. Okay, does anybody want to help me with this? Is the first statement true?
Yes.
Second one?
No.
Third?
No.
And the fourth?
Yes.
Perfect, thank you, right? You guys are quick. So the number of channels in any filter equals the number of input maps or input channels, and the number of filters equals the number of output channels, right? And so then we saw that the convolutional layers are followed by pooling layers. They may or may not alternate with convolution. You're never going to have two pooling layers, consecutive pooling layers, but you can have two consecutive convolution layers. And you have different forms of pooling. Max pooling selects the largest from a pool of elements. And pooling is performed by scanning the input with the pooling filter. So we saw some pseudocode for it. You can have mean pooling, where instead of selecting the largest element, you could just average all of the elements within the window and scan in this manner. So mean pooling, again, looks like standard convolution, right? Except that it is in the standard convolution, you were simultaneously scanning all of the previous layer channels, and the filter weights were learned. Whereas when you're performing mean pooling, you're just going to be looking at just one channel, and the filter weights are fixed. They're equal to 1 over n, where n is the number of elements in your window. So here this would be 1 over 4, right? And we saw pseudocode for it. We also saw a different kind of operation, resampling, where we would try to increase or decrease the size of the output. So downsampling was where we tried to reduce the size of the output by a factor s. And the way we did it was simply to drop every s minus 1 rows and every s minus 1 columns between any two rows and columns. And if we wanted to increase the size of the output, this was upsampling. We did this by introducing s minus 1 columns of zeros or s minus 1 columns of rows of zeros. So this was downsampling. If you wanted to downsample this input by a factor of 2, you basically deleted every second row and every second column, and then compacted the rest down. And so this was your downsampling layer, right? And if you wanted to upsample, you just introduced s minus 1 rows and s minus 1 columns of zeros between elements. Now we also saw that typically downsampling is merged with the operation of the previous layer simply by increasing the stride. So a convolution followed by a downsampling layer can be performed by convolving with a stride. Pooling followed by a downsampling layer can be performed by pooling with a stride. But again, it's very convenient and mathematically more simpler to think of pooling with a stride or convolution with a stride as convolution followed by downsampling, because the backpropagation rules for downsampling and convolution are easy, but the backpropagation rules for convolution with a stride tend to be a little more tedious. So also, upsampling is almost always followed by convolution, because there's no point in simply having a collection of zeros in your maps, right? So convolution smears this information out. Yes?
Upsampling is like kind of padding, just that it's
Padding is typically represented, when we speak of padding, you're adding stuff at the boundaries. You're sticking stuff in between. So that's why we use the term upsampling, right? This is standard signal processing terminology. And then you followed by convolutions. And this upsampling followed by convolution is also often called convolving with a fractional stride. So this would be like, so if I were upsampling by a factor of 2 and then convolving, then this is, since the size of the output, the number of layers and columns is increasing by a factor of 2 in this case, it's like saying I'm striding by half a pixel. So the terminology that you often hear is convolution with a fractional stride, right? So again, although resampling operations are generally merged with the convolutions or pooling in the previous layer, or it's very, as particularly downsampling, it's always useful and convenient to think about all of these operations as separate. Both upsampling and downsampling must be separated from the preceding convolution or pooling operation and the succeeding operation, and treated as a separate operation for simplicity of backpropagation rules. So in all of the backpropagation rules, we went through a whole example of how we can put all of these things together in the last class. Now, in all of the backpropagation rules that I'm going to be talking about in the next hour and exactly an hour left, right, I'm going to assume that the convolution is performed with a stride of 1. If we run out of time today, we're just going to pick up where we left off and complete it on Wednesday. Now, here's the last thing we saw. We saw that in a typical image classification task, assuming that you're performing max pooling in my example, we'd have a collection of images, one channel per color. We'd stack them up, and then this was going to be followed by a series of convolutions and poolings. And the output of the final layer was eventually flattened, and the flattened values were put through a multi-layer perceptron for your final classification. So the parameters that had to be learned were the parameters of the final MLP itself and the parameters, all of the filters that were used for the convolution. Now, training over here we saw is as in the case of a regular MLP, the only difference being in the structure of the network. You'd have training examples of the image and the class. You define a loss, for which you define the divergence between the actual and target output of the classifier. And then the actual loss is going to be the average divergence over all of your training data. The network is trained to minimize this loss. Now, the way we did this, for this, we needed to be able to compute the divergence between the actual and the target outputs for each instance. And the actual loss itself was the average of this divergence over all of your training instances. For backpropagation, for gradient descent, we needed the derivative of this loss with respect to the individual parameters, which are the individual parameters of all of the filters of the network. And so this means to be able to compute this, we need to be able to compute the derivative of the divergence for individual training instances with respect to filter parameters. And this is easy enough. If you were just we've derived how to perform backpropagation for MLPs. So for the final flat layers, you could just use your standard backpropagation rules to compute the derivatives at the input of the final flattened layer. And then, of course, we know that the final convolution layer gave us a bunch of values, and these were flattened into a vector. So for example, in the first 4 elements in the flattened vector would be the, in this picture here would be the 4 elements in the final layer of the convolutional component of the network. So when I perform backpropagation, I would be able to compute the derivative of the loss with respect to these terms, and this can now be folded back into the same shape as the maps that we got at the output of the final layer of the convolutional portion of the network. And so once we have those, we can now propagate those derivatives backward to compute derivatives for the rest of the network parameters. So here's where we finally stand, that we can assume that we actually have derivatives for all of these terms, which are the outputs, the activation maps of the eleventh layer. So if I have the derivatives of the divergence with respect to these guys, our job is now to figure out how to backpropagate those derivatives all the way backwards, both here, both from here, from the activation map to the affine map, and the affine map back to the previous layer, the previous channel's outputs, and also the derivatives of the divergence with respect to filter parameters. So going back here, again, we have computed the derivatives with respect to, if I'm looking at a pooling layer, same thing. We'd have computed the derivatives with respect to the output of the pooling layer. We have to figure out how to propagate those derivatives backward to compute the derivatives with respect to the input to the pooling layer. So here are all the things that we need to compute. We can assume that we already have the derivatives with respect to the elements of the maps output by the final convolution layer of the convolution portion of the network. So now we must backpropagate those derivatives, which means that for convolution layers, we first need to be able to compute the derivatives of the affine maps, assuming that we have the derivatives of for the activation maps. Then the derivatives for the affine maps must be propagated backwards. And we need to be able to compute the derivatives for the previous layer outputs and also for the intermediate filters. For the pooling layers, given the derivative of the output for the outputs of the pooling layer, we need to be able to compute the derivatives for the input of the pooling layer. So let's look at the convolution layers first, because they are the more complicated ones. First, if I have the derivatives for the activation maps, how do I compute the derivatives for the affine maps? That's easy, right? So within each layer, what we find within each convolution layer, first you have these affine terms computed, the z's. These are all of these z channels, these z maps. Then we apply a pointwise activation to each of the elements in the z's to get the corresponding y's. So if I assume that I have the derivative of the divergence with respect to these guys, I just need to be able to push these back to this element over here. And we know that within any layer L and within any channel, say M, the value at xy is simply whatever activation you have to the affine value in the mth channel of the lth layer at position xy. So this one is a pointwise computation that we perform. So if I have the derivative of the loss with respect to this y, then the derivative of the loss with respect to the corresponding z is simply going to be the derivative of the loss with respect to y times f prime of z. This is just a standard derivative rule. And the z, of course, has been computed going forward. So propagating derivatives back from the activation map to the affine map is quite trivial. Can you shut your laptop? Okay, right. So this is easy, right? So let's assume that we've taken care of the first bit. Any questions over here? This was the easy bit, right? The more challenging one is, once I have the derivatives for z, how do I compute the derivatives going backwards for the previous y and the filters in the middle? And this is quite fun, actually. So here's what I've got. In the forward computation, I can assume that I've taken the y's output by the previous layer, convolved them with the filters for the next layer, and obtained the z's. So now, going backwards, I can assume that I now have the derivative of the divergence with respect to the z. I must push that derivative back to compute the derivative for y and the w. So let's look at this first guy. How do I compute the derivative for y? So here again, here's what we've got. I've managed to propagate my derivative for z, for the divergence. The derivatives backward until I have the derivatives for the divergence with respect to the z's. And from here, I must now push these derivatives back and compute the derivative with respect to the y's from which the z's were computed, right? So let's see how this goes. Now I know that in order to compute any particular output channel over here, this is obtained by convolving the corresponding filter. So to get the nth output channel, I'm going to be convolving the nth filter with the collection of input maps, the input channels, right? So every input channel is influencing the nth output map, and it influences it through the corresponding channel of the nth filter. That making sense, right? And so also, so I'm just simplifying this. Here's a simplified diagram. The nth channel of the L minus 1th layer, the mth channel of the L, I have some, yeah, the mth channel of the L minus 1th layer influences the nth channel of the Lth layer through the mth channel of the nth filter for the Lth layer. I mean, there's a lot, there are a whole lot of indices, okay? So I'm not going to spend any time on the indices because the pictures must tell the story. I'm just introducing the indices so that you know what we're speaking about, right? Now, so also now every input channel influences every output channel through the corresponding filter. And every one of these output channels in turn eventually influences the divergence, right? So if I want to compute the derivative of the divergence for any particular input channel, these are all the influences that I must consider. Every input channel is influencing any given input channel is influencing every output Z channel, and every one of those is influencing the divergence. So if I want to compute the derivative of this divergence with respect to Y, I'm going to have to sum a whole bunch of terms. I would have to compute if I want to compute the derivative of the divergence with respect to Y, I'd be summing over all of the output channels. And what I would sum is the derivative of the divergence with respect to Z times the derivative of Z with respect to Y, right? So here's what I would have. So I'm going to have to compute the derivative of the divergence with respect to Z. This I can assume I already have since I'm backpropagating, right? And so the term that I need to compute is what is the derivative of any particular Z with respect to the input Y.
What about the weight?
So we haven't gotten to the weights yet, right? So now that means I need to compute the derivatives for all of these Z's with respect to Y. Let me focus on just one of them. The derivative for the nth output channel with respect to the mth input channel, okay? Just this one guy. So here, let's see how to understand how this derivative works. Let's see how this guy was computed from this one here, right? So to compute that, we had a filter. To compute the nth output channel, we had the nth filter. The nth filter had many channels itself. So the contribution of the mth input channel was obtained from the mth channel of the nth filter, right? So let's assume that this is that filter, the one that's shown in yellow. And now, if you look at any particular element of the input channel, the one that's highlighted in red over here, which of all of the output values does it influence? So when the filter is placed on the top left corner, this guy results in the computation of 4, right? If it's moved forward by 1, this guy results in the computation of 3. So if you look at that highlighted term 1, that one actually is used in the computation of these 4 elements of the output as the filter moves, right? Is that making sense to you guys? You see what we're talking about? And so each Y term influences several Z terms over here. And in fact, each Y term is going to influence several Z terms in each of the output channels. And so if I want to compute the derivative of the divergence with respect to any given Y term, so if I want to compute the derivative of the divergence with respect to the Y term at the location xy, I have to sum first over all of the output channels. Within each of the output channels, I have to sum over all of the elements of that channel, because each y term potentially influences all of them, right? And at each of those positions, I want to compute the derivative of the divergence with respect to that z location times the derivative of that z with respect to the y. That makes sense to everybody, right? And of course, this term here is what we need to know, because we are assuming that the derivative of the divergence with respect to the z's has been obtained during backpropagation, right? So what is this guy? What is the derivative of any particular z over here with respect to yxy? So let's look at this guy. Now, what is the derivative of zx prime y prime with respect to yxy? I mean, I'm overloading the symbol y, okay? So for that, let's consider this one term. So let's say, let's consider any particular x prime y prime. So the output map, I'm showing you a single output map, and I'm showing you a single element of a single input channel, specifically the 2,2 location of the input channel. I'm showing you, so since we are computing the nth output channel, I'm showing you one map from the nth filter. And since I'm considering the mth input channel, this guy is the mth channel of the nth filter. So, right? Now I'm using color coding and indices to illustrate what is happening. So if I look at the filter, I'm representing not merely the index of the location of the filter, I'm also representing the value using a color. This is to give you a clear cue as to what is happening over here. We're going to need both the color and the index. Now, to compute the 0th element of z, I'm going to be placing this filter starting at 0, 0 on the input channel, right? If I do so, which element of the filter sits on the 2,2 element of the input when you're computing the 0, 0 output? The 2,2 element of the filter, right? So if I look at the z0, 0, the contribution of y22 is through w22, right? So z0, I'm putting a plus equals. Is that making sense to everybody? Okay, so now if I want to compute the z10 position, I have slid the entire filter forward by one step. If I slide it forward by one step, now which filter element multiplies y22 to compute z10? y12, right? w12, right? So I have w12 multiplies y22 to give you z10, right? And I slide it one step forward again. So which filter element now multiplies the y22? 0, 0, right? And so you can see this, right? Does anybody see a pattern in the indices? Does anybody see a pattern in the indices? Yeah. Give me a formula, right? So here, it's a reverse filter. Zx prime y prime for any x prime y prime is y22 times w of 2 minus x prime 2 minus y prime, right? At every position. What happens is that the index of the filter and the index of z add to give you the index of y. Can you see that happening over here? Right? You can double check. At every single location, this will happen. So here, for example, let's go back to the beginning. So this one, 2, 2 plus 0, 0 gives me 2, 2, right? Over here, 1, 2 plus 1, 0 gives me 2, 2. 0, 2 plus 2, 0 gives me 2, 2, right? I can keep going this. So 0, 1 plus 2, 1 gives me 2, 2, and so on. So when I get all the way to the bottom, here's the generic formula. For any given xy location of y, the contribution of the xy location of y to the x prime y prime location of z is through w of x minus x prime, y minus y prime. That making sense to all of you guys? Must make visual sense, right? So if this is the case, then here's what happens. The derivative of z x prime y prime with respect to yxy is the weight of, what is it? X minus x prime, y minus y prime. Does that make sense to everybody? Right? And so I can now plug this into my formula. Very easy. Here's what I had. To compute the derivative of the divergence with respect to any element of any given channel, I had to sum over all of the output channels. And then within the output channels, I had to sum over all of the elements of that output channel. And at each location, I had to multiply the derivative of the divergence with respect to the corresponding z value times the derivative of that z value with respect to the input y value, right? And what is dz x prime y prime over dx, yxy, dyxy? So because we said that the index of the weight and z sum to the derivative index of y, right? So this is simply going to be wx minus x prime, y minus y prime, right? And so here's an easy formula, right? By the way, this is 723, 724, and 725. Okay, these ones are easy. Does anybody want to help me with the first question? True or false? Second one? Also true, right? In order to compute the derivative at a single affine element via y, we must compute the, that should have actually been activation element. We must consider the contribution of every position of every affine map at the next layer, right? And the derivative for a single element y will require summing over basically every z map of the next layer. So that's basically what we saw. And so here is the formula that we got. If you simply implemented this formula straight up, you'd be able to compute the derivatives of the output with respect to the input y's. It's very simple, right? But then this is actually a convolution. And can you see why this is a convolution? Anybody? We are summing over the x's and y's, right? So I can actually throw this at you and tell you that it's a convolution, but then let's actually visualize how this is a convolution, how this works. So I'm going to go back to my picture, right? Now look at the element at z00. And now we will actually begin looking at the color codes, right? So if I look at the element at z00, y22 multiplies the red element of the filter to compute z00. So I've actually painted z00 with the color red to indicate which filter element was used in computing z00. Can you see that? Okay. And so now if I want to compute the derivative of the divergence with respect to y22, I'm going to be multiplying the derivative of z00 by the red value, right? Because the red value is what multiplied y22 to compute z00. That makes sense? Right? And so also, if I take one step forward, y22 was multiplied by the pink value to give you z10, right? So if I'm computing the derivative of the divergence with respect to y22, I'm going to be multiplying the derivative of the divergence with respect to z10 by the pink value. That makes sense to everybody? Right? And so also, if I look at Z20. Z2, to compute Z20, the green value was, the green weight was multiplied by 22 to give you Z20. So going backward, the derivative of the divergence with respect to Z20 must multiply the green weight to compute the derivative with respect to Y22, right? And so if I go through all of these in a row, here's what we find. Here are all of the Z values. So every one of the derivative of the divergence with respect to every one of these Z values must be multiplied by the weight shown by the corresponding color in order to compute its contribution to the derivative of the divergence with respect to Y22. Make sense? Right? Visually? And so if I have, what this means is that if I have the derivative map for y, meaning I have the map of the derivatives of the divergence with respect to each of these y elements. They are also arranged in the same shape as z itself, right? That derivative map is now going to be multiplied by the filter values shown, and they must then all be summed to give you the derivative with respect to y22, right? What do these filter values look like when you look at the original filter? What is the relationship between the two? Can you speak up, please?
It looks like 180-degree rotation.
Is it a 180-degree rotation?
Or
What is it like? Somebody tell me. It's flipped vertically and flipped horizontally, right? The entire filter is flipped and flipped. Can you see that? Right? And so here's what happened. To compute the derivative for y22, I took this filter and flipped it vertically and flipped it horizontally so that this 0, 0 element now ended up over here, and the 2, 2 element now ended up over here, right? And where did I place the 0, 0 element? So if I think about this, I placed the 0, 0 element on Z22, right? And did an inner product. And that gave me the derivative for y22. That makes sense? Can you see that? Right? Or in general, if I flip the filter top to bottom, left to right, now the 0, 0 element is at the bottom right, correct? If I place that on the xy position of the derivative maps for the z's, and then compute the inner product, I'm going to get the derivative for the corresponding yxy. Does that make sense to everybody? Right? And so it's very pretty, right? So questions? Yeah.
Question in Piazza, did all contribute to dy L-1 and L2?
So in this case they did, right, as you can see. Because you can see there are 9 filter elements, and every one of the filter elements multiplied a corresponding z, right? Or multiplied a corresponding d div over dz to give you its contribution to d div over dy. Okay. And so how does the whole thing become a convolution? So let's say I had an input map which convolved this channel. So this is the mth input channel. It convolved the mth channel of the nth filter to compute the nth output channel, right? So then going back, I can assume that I have the derivative of the divergence with respect to the elements of the nth output channel, right? Now here's the thing. Here's a very simple rule that you must never forget. So let's say I have a function . So let's say I have an input of size L cross M. And this input goes through some box which computes a scalar derivative L, scalar divergence L. What is the size of the gradient of L with respect to the input? What is the size? Anybody? Come on, guys. Can you speak up? I can't hear you. What is the size of the gradient of the loss, scalar loss with respect to the input here? Can you say it aloud? Okay, L cross M. Can everybody say that? L cross M. Right? You're going to have as many terms in this derivative as the number of inputs, because every one of the inputs has affected the loss, has it not? Yes. Correct? And so here's the other thing. Suppose I have some M cross N input going into some box, and which gives you some A cross B output, which is finally used to compute the loss. If I go backward, what is the gradient of the derivative, gradient of the loss with respect to this guy? What's the size? A by B. What about this guy? What is the size of the gradient of L with respect to this guy? M cross N, right? You're going to have as many terms in the derivative as the number of values. Every one of them influences the loss. The fact that they're being merged does not matter, correct? So over here, going back, this map was smaller than this guy, was it not? Going forward, why was it smaller? Why was it smaller? Summed. Why was this smaller? The result of convolution. You lost things at the boundary, right? If the filter size was M cross M, how many rows did you lose at the boundary? Can you speak up? It's true, right? If I had an M cross M filter, how many rows did you lose at the boundary? Can everybody say M minus 1? Right? And how many columns did you lose? And that's because we had this, if I had something of this kind, so if I had an input, which is N cross N, and my filter was M cross M, the filter could step forward only N minus M times, then you had the first position, right? And so the output was N minus M plus 1, which meant that you lost M minus 1 rows and M minus 1 columns, correct? That makes sense? Do you remember this? Yes. So when you're computing the derivatives going back, what do you expect will happen? You're going to get back those guys, right? So here, the derivative size here, whatever the size is, when you go back here, you're going to add back N minus 1 rows and N minus 1 columns. That makes sense to all of you? Right? It must happen, right? And so how can I do this now? Remember this. This guy is, say, 3 cross 3. My filter is 3 cross 3. How do I make this 3 cross 3 derivative go back and become a 5 cross 5 derivative? Pad it. How much do I pad it? Am I going to be padding it by M cross 1? Am I going to be padding it by M minus 1? If I pad it by M minus 1 and convolve it with a filter, what will happen? So I had 3 cross 3, right? So my output was 3 cross 3. If I pad it with M minus 1, that's going to become 5 cross 5, correct? So, but then this 5 cross 5 is going to be convolved with a 3 cross 3 filter. What is the output size going to be? Can anybody say it aloud? What is this output size going to be? 3 cross 3. So is it enough to pad it with two elements? No. How much should I pad it by? Double that. That makes sense to everybody? Right? I have to make this guy 7 cross 7 so that when I convolve it with 3 cross 3, I end up with 5 cross 5. That makes sense to everybody? Right, and so here's what we are going to do. I'm going to pad it all around with zeros. If I have a 3 cross 3 filter, I'm going to pad it with 2 rows and 2 columns of zeros on every side. That makes sense to everybody? And then, I'm going to flip my filter left to right, top to bottom, and then place it over here. And now the 0, 0 element of the filter is sitting on the 0, 0 element of my z, right? Forget about the padding, right? And the resulting inner product is going to give me the 0, 0 element of the flipped filter. And the resulting inner product is going to give me the derivative for y0, 0, right? And then I'm going to slide this one step forward. And now this is going to give me the derivative for y01, y02. I've run out of z at this point. But I've run out of z for the leading edge of the filter, but the trailing edge of the filter still has z, right? So I can keep stepping forward. And this is going to give me the derivative for y04, right? And then I can take yet another step forward, and that's going to give me the derivative for the next y. What happens if I take one more step? There's nothing left. I ran out of things, right? So now I have to go back here. And this is how I would compute my derivative. So now, do I stop here?
No.
I can go back here, go down here, right? And then I can go down here. And this is when I finally stop. This makes sense to everybody?
Yes.
Right? But then this was just one z value, right? This was just one z map. But then we saw that each channel of the previous layer influences all of the z maps, correct? And so in order to compute the derivative, what you would do is, remember, every channel over here influenced every output map, but what did it influence the corresponding output map with? If I have the mth input channel, the mth input channel influences every output channel, right? But it influences every output channel through the corresponding filter, but specifically through the mth channel of the corresponding filter. Because only the mth channel of the filter convolves the mth input map, right? That makes sense to everybody? And so to compute the derivative of the divergence with respect to y, here's what I'm going to have to do, right? So I'm going to take these guys, all of these guys, the mth channel of all of the filters. And then I can just create a new filter with just the mth channel of all of the filters. Make sense? Right? And then those guys can now be flipped in along both axes. And now the corresponding z's are going to be padded with zeros on every side. And then I'm simply going to convolve these guys, these flipped filters, simultaneously with all of the z's. And this is what is going to give me the final derivative for the y map. This makes sense to you guys? Right? So the whole thing is a transpose convolution. Why is it transpose convolution? We did two things. We took the filter and transposed it in every which way. If I think of the filter as a giant matrix of channels, going forward, we are looking at the columns of channels. Now we looked at a row, right? But we didn't stop at looking at a row. Within the row, we flipped each term horizontally and vertically. So we transposed it in every which way. And then we multiplied we zero padded the output derivative maps and then convolved. And that gave us the derivative for the input channel. Question?
So when you do like normal convolution and you choose padding, like you could theoretically choose any value, but here if you chose any value besides 0, you basically have the derivative of those padded values.
Because the corresponding input is going to have no influence, right? So this is basically what the derivative rule going forward looks like, right? Everybody with me? Okay, so, and if you actually, so basically if you check, the size actually works out, right? And now if you zero padded going forward, then going backward, you're going to get the derivative for the zero padded input. You're going to have to throw the boundary values out, yes?
In June, they're asking if you can re-explain why the one got flipped for backprop.
So, okay, folks on Zoom, do you understand why the individual filter got flipped? We spoke of this, right?
Okay, know that.
So going back all the way here, that's way back when, right? So look at how this input is the filter to the left. And you can see at each z value which filter element was used in computing it. And if I look at it this way, you can see that to compute, when you look at the influence of y22 in computing any z element, then the arrangement of filter terms is basically a horizontal and vertical flip of the filter itself. So on Zoom, did that make sense? Please do speak up so I can know, right?
Yes.
Yeah. So basically, if you look at how y22 influenced z, you can think of it as, so when you're going backwards, if you look at how the derivatives work, you would see that the derivative of z22 multiplies the pink element of the filter to give you the derivative for y22. The derivative for z12 multiplies the brown element to give you the derivative for y22, and so on. So basically, it's like saying that I've flipped the filter left to right, top to bottom, and placed it starting at the 2,2 position, and performed an inner product to compute the derivative for y22. Or more generally, I'd be flipping the filter and then placing the 0, 0 element on the xy component of the derivative map for z, and then performing an inner product to compute the derivative for yxy, right? Does that answer your question on Zoom? I'm assuming the answer is yes, okay? So, any questions in class? Right. So this one is not 637. What is this one? 726. This is at 726. Okay, does anybody else want to take the first one? Is the first statement true? Yes or no?
Yes.
Second one?
Yes.
Third? And the fourth? Okay. So basically, to compute the derivative with respect to the mth activation map of the lth layer, we must select the mth channels of all the filters, and they must be flipped left, right, and up, down. They must convolve the derivative maps of the next affine layer, right? The derivative maps themselves don't need to be flipped. So far so good. And so this can be computed by convolution with a flip filter. I have some pseudocode for it. So we figured out how to compute the derivatives for y's, right? But then the filter, that's the key bit. That's what we want to learn. How do you compute the derivative with respect to the filter itself? Now to see this, I'm going to show you this some really bad animation by MATLAB because it keeps changing the color. Maybe someday I'll actually fix this. But the point I'm trying to make is that if you consider the central element of the filter, the central element of the filter is used in the computation of every single element of Z, right? Each element of the filter affects every single element of Z. So if I were to look at this, something like this, right? Let's say, I painstakingly changed these figures and my machine didn't update. So I'm going to use the older figure. Anyway, so just consider that highlighted pink region, pink element in the filter. The highlighted pink element in the filter, which is going to be in this case the 1, 2 element of my filter, it multiplies y12 to give me z00, as you can see, right? It multiplies y22 to give me z10. It multiplies y32 to give me z20, right? You can see how which element of y it multiplies to give you which element of z. So once again, do you see a relationship over here? It's the same one as before, right? What is the relationship we see? So we always had that this filter element plus this guy gave you y, correct? That's what we saw. But now since our focus is on the filter, I can fix the filter term and say, you know, the zxy and the filter for filter element 1, 2, it multiplies y of x plus 1, y plus 2 to give you zxy, right? Does everybody see that? Right. So, or more generally, I can say that for any x prime y prime element of W, I'm going to say, or for any ij element of W, it multiplies y x plus I, y plus j to give me zxy. So going backwards, if I have the derivative of the divergence with respect to the y element, to the z elements, right? So when I'm performing my backprop, I'm assuming that I already have my derivative with respect to z. So what is the derivative of z with respect to wij? So what is the derivative of zxy with respect to wij? You see what is happening? You see the formula over here? It's simply y of x plus I, y plus j. That makes sense to everybody? Right? And so now, here, now let's look at any particular weight. So the W12 element over here multiplied y12 to give you z00. It multiplied y22 to give you z12, right? z01, and so on. So those arrows show which y element, all of the arrows refer to W12, okay? And they show which y element W12 multiplied to give you which z element, right? So if I want to compute the derivative with respect to W of the loss with respect to W12, I'm going to multiply the derivative of the divergence with respect to the z at the end of the arrow with the y at the beginning of the arrow, and then sum over the entire region. That makes sense? Right? So visually. And I'm going to have to sum over all of those xy guys. And so here's what I'm going to do. So now the derivative of the divergence with respect to z is already available. What is the derivative of the z in general, zx prime? So if I want the derivative of the divergence with respect to any wij, I'm going to have to sum over the entire. Now remember that wij, a filter, a particular channel of a particular filter only affects a single output map, because the filter is output map specific and only involves a single input map, right? Because a channel of a filter, the index of the filter decides the output, the channel of the filter decides the input. So now so you only have to sum over the individual terms, right? So you're going to have to sum over the entire output map, but then what you'll be summing is the derivative of the divergence with respect to the zeta times the derivative of the z with respect to the filter term. This formula making sense? Right? And what is the derivative of zxy with respect to wij? Guys, y what? Can you say, speak up please, you're mumbling, somebody? Right, that's basically what it is. We just showed you what it is, right? And so this, if you simply implemented this formula, you're going to be able to get the derivative of for the filters, right? But then it turns out that this is also a convolution. Why so? So here, to compute the derivative for W12, what have I done? To compute the derivative for W12, I took the derivatives with respect to all of the z elements and multiplied each element with the corresponding y element shown at the head of the arrow, right? So I'm summing over the entire z's, but what I'm effectively doing is placing that derivative map for z on top of the y and just performing a component-wise product and summing up. Can you see that? Right? Similarly, if I want to compute the derivative for W00, W00 multiplies Y00 to give you Z00, right? And so once again, if you look at the arrows, if I want to compute the derivative of the divergence with respect to W00, this is like saying I'm going to be multiplying the derivative of the divergence with respect to this Z with this guy, plus the derivative for this Z times this guy, and so on. So it's like saying I'm placing the derivative map for Z starting at the 0, 0 location of Y, performing a component-wise product and summing the lot up. And that's going to give me the derivative for W00, right? Does that make sense to everybody? Right, and so effectively, what does this mean? This means that this term too is a convolution. Effectively, the derivative of the divergence with respect to any channel of any filter, you're just convolving the derivative map for the corresponding output channel with the corresponding input channel. That's it. So pictorially, here's what we're doing. This is what we had going forward, right? I had all of the input maps convolving with each of the filters to give you the corresponding output channel. But then if I want to look at a particular channel of a particular filter, that only invokes one input channel and computes one output channel, right? So only these two terms at the two ends of the arrow are going to be involved in computing the derivative for that particular channel of the filter. Everything else can be ignored, right? And so we're going to be interested in the derivative map for the output channel and the corresponding input channel. And here's all we will do. I'm going to take the derivative map of the output channel and simply convolve it with the input channel. And that's going to give me the derivative for the filter. That makes sense to everybody visually, right? And the sizes will match. Why? Because if the input is size 5 and the output is size 3, what is the size of the derivative? What is the size of the convolution? 3. And what is the size of the filter? Also 3. They will all match up, right? You can see that they match up. So overall, I'm not spending a lot of time with the math, with explaining the arithmetic. I'm hoping the figures make sense. So if I want to compute the derivative for a particular filter, right? That filter had as many channels as the number of input channels, and it convolved with all of the input channels to compute a single output channel. Going backward, I can assume that I have the derivative map for the output affine channel, right? And so all I will have to do is to convolve this term with each of these input channels to get the corresponding derivatives for the entire filter. That makes sense to everybody? Right? So very easy. So the entire thing is still a convolution. So this one is 727. This is our last poll. I'm going to go a minute or so over, guys, just so that I can try to wrap up. And even if I don't, it shouldn't really matter. We have it mostly covered. Okay, anybody want to take the first statement on Zoom? True or false? On Zoom.
True.
And the second one?
False.
Thank you. So does everybody agree here? The derivative for the mth channel of the nth filter is obtained by convolving the mth input layer, input channel, by the derivative map for the nth affine channel, right? And there's no flipping or transposing involved. So to compute the derivatives for the input, we need to transpose the filter. To compute the derivative for the filters, nothing is required. Now, I have some. So all of this looks very complicated, right? But then it turns out that, when you begin writing the math, when you begin visualizing things, it's kind of complex. When you think of it in terms of code, sometimes things just become trivially simple. So here's what we had. When we went forward, here we have these standard rules. If I apply an activation sigma to an affine term z, then if I have the derivative of the loss with respect to y, the derivative of the loss with respect to z is simply dl over dy times sigma prime, right? Similarly, if I have z equals wy, if I have the derivative of the loss with respect to z, then dl over dy is simply w times dl over dz, right? And so also dl over dw is simply y times dl over dz. This is just a straightforward derivation rule. Just using these two rules, I can manipulate my code trivially and get the entire backpropagation done without understanding the math one small bit. And how is that? We remember that this is backpropagation, right? So when I'm going forward, what am I doing? If I go through all of my computation, I'm going through the layers. Within each layer, I'm scanning the input. And then within each, at each location, what am I doing? I'm scanning the area of the filter. And over the area of the filter, I'm multiplying the filter value with the underlying channel value and then summing them all up. And then once I've done this summation over the area of the filter, this is for each filter, I'm just applying an activation function to it, right? Observe the order of the indices and the order of the operation. All I need to do is to reverse everything. I flip the order of the indices within each layer. So where I was going from 1 to L, I'm going to go from L back to 1. That's backprop, right? But then within each layer, instead of going from 1 to the end of from the left to right, top to bottom, I go from bottom to top, right to left. So that's all I did was flip the indices, right? And then here, at when the entire multiplication was performed, there was this. When we had summed over, for each filter, when we had summed over the entire face of the filter, we finally applied an activation, right? So going backwards, I can just move this guy from the bottom to the top, this application of the activation. And I can say the derivative with respect to z is the derivative with respect to y times the underlying, times the derivative of the activation. So once that is done, here's what we did. Earlier we had z equals w times y, right? Within the loop, I replace that by dy equals w times dz, dw equals dz times y times dz, right? So I just use those two simple rules. I flip my code left to right, bottom to top, change the order of the computation and replace two rules, and the whole thing will just work. I don't even need to know how this works. This will just give you the correct answer. And so this means that if you performed your computation with a stride going backward, you'd just be flipping the indices and you'll be performing your computation with a stride going backward. If you perform a computation with a stride going forward, you'll be flipping your indices and performing your computation with a stride going backwards, and everything is just going to magically work. So take a look at the slides. And so we've seen how to compute derivatives with respect to both the z's and the y's. We'll pick up from this at least in the next class. Any questions? Any questions on Zoom? If not, thank you.